So the third question on 2.4 is fairly straightforward. It's everything that you've already done. There's really no difference in the approach or the process or anything. You guys have already learned it. So what you're going to be using is the horizontal asymptote. So remember, a horizontal asymptote is what the graph approaches. It doesn't cross it. It doesn't actually touch it, but it approaches it. So that's the question that they're asking. So the question on question 3 is, you have a study on the speed of muscle contraction in a certain species of frogs under various loads. Researchers found that the speed of contraction decreases with increasing loads, which makes sense, right? The more pressure you put on, the contraction slows down. In particular, they found that the relationship between speed of contraction, v, and load, x, is given by this function. So as you notice, it's a rational function, right? It's actually an average because we took the total and we divided it by the number of loads in grams. So it's a rational expression. Our domain is x is greater than or equal to 5. So that means that the number of grams is greater than or equal to 5. That's how much load we're putting on this muscle to do the study. So A is asking, what does the function approach as x increases? Anytime you see it in that format, what they're asking is, what's the horizontal asymptote? That's what it's asking. What is the graph approaching as x gets bigger and bigger and bigger? Well, it's going to approach your horizontal asymptote. So this goes back to those three rules. So a horizontal asymptote is always based on the leading exponent. In this case, my leading exponent is right here. I don't have to worry about the 21. It's whatever is my highest exponent. Okay, that's my leading exponent. So I have x to the first, x to the first. So the 3 rules again. If the top is equal to the bottom, okay, in this case, that's the truth. We have x to the first over x to the first. Those exponents are equal to each other. Then my horizontal asymptote is whatever the ratio is. So in this case, the ratio is 0.07 over 1. So my horizontal asymptote is approaching 0.07. Okay, so that means my graph is coming to approaching 0.07 on my graph, but not touching it. That's what it's approaching. The second rule is if the top is greater than the bottom, then there is no horizontal asymptote, so you don't have to worry about that. And the third one is if the top is less than the bottom. So when I'm talking about I'm talking about the exponents. If the top exponent is less than the bottom exponent, then the horizontal asymptote is at y equals 0. So it is your x-axis. Okay? All right, so whenever it's asking for what is it approaching, it's approaching a horizontal asymptote. You're going to use these 3 rules to decipher where is it approaching. All right, and then the second one is sketch a graph. So the graph, again, use Desmos.com. That one works really well. If you have a graphing calculator, a TI-84 or TI-83, you can use that to help you with this. But you do have an idea of what your graph looks like. So what we can do, if you don't have the graphing calculator, is we know that our x values are equal to or greater than 5. So we can plug 5 in. So we're going to plug 5 into this function. So 21 plus 0.7 times 5, all divided by 5, and have it spit out an answer. So 21 plus 0.07 times 5, all divided by 5, and I get 4.27. Because it's any number greater than 5, I can do 10. So I take out my 5 and put in 10, take out 5, put in 10. So I have 21 plus 0.07 times 10, all divided by 10, and I get 2.17. Keep going. If I do 30, and again, x values, you can plug in whatever you want. Just make sure it fits the domain. So 21 plus 0.07 times 30, all divided by 30, is 0.77. So as you can see, as my x values get bigger, my y values are getting closer and closer and closer to 0.07. So watch this. 21 plus 0.07 times 100, all divided by 100, is 0.28. So do you see it? It's getting closer and closer and closer to that 0.07. So when you're graphing, again, here's 5. 5 is about 4.27. Here's 10. 10 is about 2.17. Here's 30. 30 is about 0.7, so there's 1, so it's about here. And then we come out here to 100, and 100 is about 2.8, so a quarter of the way. Okay, and our horizontal asymptote is, I'm trying to do this straight, is at 0.07. Okay, so we know our graph is going to approach but not touch 0.07, and that's our graph. Okay, again, Desmos will confirm everything that you need, but it's pretty easy to graph because you know the basic shape. You know it's that curved shape that you're looking for, and you know it's approaching 0.07 but not crossing 0.07, and that's number 3.